Welcome, calculus students and seekers of truth. In the last video, we ended on a note of something like this, that, if f prime of x is equal to ax to the n, then f of x, its antiderivative, must be equal to a over n plus 1 x to the n plus 1. But we said that this only works if n is not equal to -1. So let me show you just a little bit about what happens when n is equal to -1. So let's say I have a function whose derivative is equal to x to the negative first. So bearing in mind here that that n here is equal to -1, right? Ax to the n, and a is equal to 1. Well, if we apply what we knew before, we would have f of x is equal to, and we're going to add 1 to this exponent, so that's x to the 0th. Right? And then we're going to divide by this same exponent. So, n plus 1 here now is equal to 0. So we're raising the x to the 0th power, and then we're dividing by 0. Well, x to the 0th has no problem, it's just 1. But dividing by 0 is undefined. Okay, so that's the problem with taking the antiderivative when you have x to the negative first power. So how do we resolve this problem? We will find out a little bit later in this video, although I will hint at it for you that, if you look at this, x to the -1 is really nothing more than 1 over x, right? And those of you who are paying very close attention and really understand how derivatives work, you should be able to find the antiderivative to this, even though it's a little bit tricky. Right, but I will just leave this note here for now, and we will return to it. I want to develop some more concepts before we return to this more difficult case. So now let's look at some of the trigonometric functions, the antiderivative of sine and cosine. So if the derivative is sine, then that means the antiderivative must be negative cosine of x plus a constant. And I will prove it very, very quickly here for you on the side. These proofs are very simple. So if we take the derivative of this expression, then what we have is, remember that the derivative of cosine is negative sine. So I have negative sine of x. The derivative of the constant is gone and it goes away. And you can see clearly here that negative sign is nothing more than positive sign. So there ends the proof. Similarly, if the derivative of a function is cosine, then its antiderivative must be sine. If the derivative of a function is cosine, then the function must be sine. Because if we were to take the derivative of the function, we're taking the derivative of sine, which is equal to cosine. All right, now we will proceed to a couple more. If the derivative of a function is e to the x, then the original function must also be equal to e to the x, for the very simple reason that e to the x is its own derivative. Therefore, it is also its own antiderivative. So the proof for this as well is also very simple. If I have this function and I take its derivative, well, I'm taking the derivative of e to the x, which is itself, and then the derivative of the constant, which is 0. So then it's done. Now, if I were to have a function whose derivative is e raised to the ax, then its antiderivative, and maybe you can probably guess before I finish writing this, would be itself times not a, but 1 over a. So let's see why that works. So if I were to take this and find its derivative, so the derivative of that function, oh, I'm sorry, there should be a plus another constant out here. So the derivative of that would be 1 over a e to the ax, so it's just itself, times the derivative of the inside function. So let us not forget that when we take derivatives, the chain rule does happen. So the derivative of ax is just a, and now you can see that this a and this 1 over a will cancel each other out. So if you have e raised to a power and there's some constant in here, then that basically means that what you have, its antiderivative would be 1 over a times e to the ax. So I will end this video here, and we will pick up in the next video with the antiderivatives that somehow involve the chain rule.